Bismillahirrahmanirrahim. Today we are going to study greenhouse gases, which is a part of the previous lecture named greenhouse effect. Now let's have an introduction of the greenhouse gases. Earth absorbs some of the radiant energy received from the sun, reflects some of it as light, and reflects or radiates the rest back to space as heat. Earth's surface temperature depends on this balance between incoming and outgoing energy. If this energy balance is shifted, Earth's surface becomes warmer or cooler, leading to a variety of changes in global climate. A number of natural and man-made mechanisms can affect the global energy balance and force changes in the Earth's climate. Greenhouse gases are one such mechanism. Greenhouse gases absorb and emit some of the outgoing energy radiated from the Earth's surface, causing that heat to be retained in the low atmosphere. As explained above, some greenhouse gases remain in the atmosphere for decades and even centuries, and therefore can affect Earth's energy balance over a long period of time. Radiative forcing quantifies the effect of the factors that influence Earth's energy balance, including changes in the concentration of greenhouse gases. Positive radiating forcing leads to warming by increasing the net incoming energy, whereas negative radiative forcing leads to cooling. A greenhouse gas is a gas that absorbs and emits radiant energy within the thermal infrared range. Greenhouse gases cause the greenhouse effect on planet. Primary greenhouse gases in Earth's atmosphere are water vapors H2O, carbon dioxide CO2, methane CH4, nitrous oxide N2O, and ozone O3. Without greenhouse gases, the average temperature of the Earth's surface would be about minus 18 degrees Celsius temperature or 0 Fahrenheit, rather than the present average of 15 degrees Celsius temperature or 59 Fahrenheit. Atmospheres of Venus, Mars, and Titan also contain greenhouse gases. Human activities since the beginning of the Industrial Revolution around 1750 have produced a 45% increase in the atmospheric concentration of carbon dioxide from 280 ppm in 1750 to 415 ppm in 2019. The last time the atmospheric concentration of carbon dioxide was this high was over 3 million years ago. This increase has occurred despite the uptake of more than half of the emission by various natural sinks involved in the carbon cycle. The vast majority of anthropogenic carbon dioxide emission come from combustion of fossil fuels, principally coal, oil, and natural gas, with additional contribution coming from deforestation, changes in land use, soil erosion, and agriculture, including livestock. The leading source of anthropogenic methane emission is animal agriculture, followed by fugitive emission from gas, oil, coal, and other industry, solid waste, water waste, and rice production. At current emission rates, temperature could increase by 2 degrees Celsius temperature or 3.6 Fahrenheit, which the United Nations Intergovernmental Panel on climate change, in other words, IPCC designated as the upper limit to avoid dangerous levels by 2036. Gases in the atmosphere. There are two types of gases in Earth's atmosphere. Number one is the non-greenhouse gases. Number two is the greenhouse gases. The major constituents of Earth's atmosphere are nitrogen and 2, and its percentage present in the atmosphere is 78%. Oxygen O2 up to 21%, and argon AR, it is a noble gas, and its percentage is about 0.9%. Are not greenhouse gases because molecules containing two atoms of the same elements such as N2 and O2 have no net change in the distribution of their electrical charges when they vibrate, and monoatomic gases such as argon do not have vibrational modes. Hence, they are almost totally unaffected by infrared radiation. Some molecules containing just two atoms of different elements such as carbon monoxide CO and hydrogen chloride HCl do absorb infrared radiations, but these molecules are short-lived in the atmosphere owing to their reactivity and solubility. Therefore, they do not contribute significantly to greenhouse effect and often are omitted when discussing greenhouse gases. Greenhouse gases. Greenhouse gases are those that absorb and emit infrared radiation in the wavelength range emitted by Earth. Carbon dioxide 0.04%, nitrous oxide, methane, and ozone are trace gases that account for almost 1/10 of 1% of the Earth's atmosphere and have an appreciable greenhouse effect. In order, the most abundant greenhouse gases in Earth's atmospheres are: number 1, water vapors H2O, number 2, carbon dioxide CO2, number 3, methane CH4, number 4, nitrous oxide and 2O, number 5, ozone O3, number 6, chlorofluorocarbons CFC, about which we have already read in detail, number 7, hydrochlorofluorocarbons including HCFC and HFC, and we also have read about these hydrofluorocarbons in detail. Atmospheric concentrations are determined by the balance between the sources, which means emission of the gas from the human activities and natural system, and sinks, that which means the removal of the gas from the atmosphere by conversion to a different chemical compounds or absorption by bodies of water. The proportion of an emission remaining in the atmosphere after a specified time is the airborne fraction and is designated by AF. Now let's define airborne fraction. It is defined as the annual airborne fraction is the ratio of the atmosphere increase in a given year to that year's total emission. As of 2006, the annual airborne fraction of carbon dioxide was about 0.45. The annual airborne fraction increased at a rate of 0.25 plus minus 0.21% per year over the period 1959 to 2006. Impacts on the overall greenhouse effect. The contribution of each gas to the greenhouse effect is determined by the characteristics of that gas, its abundance, and any indirect effect that it may cause. For example, the direct radiative effect of a mass of methane is about 84 times stronger than the same mass of carbon dioxide over a 20 years time frame. But it is present in much smaller concentration, so that its total direct radiative effect has so far been smaller. in part due to its shorter atmospheric lifetime in the absence of additional carbon sequestration. On the other hand, in addition to its direct radiative impact, methane has a large indirect radiative effect because it contributes to ozone formation. Shindles et al. 2005 argue that the contribution to climate change from the methane is at least double previous estimates as a result of this effect. When ranked by direct contribution to greenhouse effect, the most important are: number one is the water vapors or clouds. Their concentration in the atmosphere is 10 to 50,000, and they contributed about 36 to 72%. Number second is the carbon dioxide. Carbon dioxide contributed about 9 to 26%, methane 4 to 9%, ozone 3 to 7% as recorded in this table. In addition to the main greenhouse gases listed above, other greenhouse gases include sulfur hexafluoride, hydrofluorocarbons, and perfluorocarbons. Some greenhouse gases are not often listed. For example, nitrogen trifluoride has a high global warming potential but is only present in a very small quantities. Atmospheric lifetime of greenhouse gases. The atmospheric lifetime of species therefore measures the time required to restore equilibrium following a sudden increase or decrease in its concentration in the atmosphere. Individual atoms or molecules may be lost or deposited to sink, such as the soil, the ocean, and other waters, or vegetations and other biological systems, reducing the excess to background concentration. The average time taken to achieve this is the mean lifetime. Carbon dioxide has a variable atmospheric lifetime and cannot be specified precisely. The atmospheric lifetime of carbon dioxide is estimated of the order of 30 to 95 years. This figure accounts for carbon dioxide molecule being removed from the atmosphere by mixing into the ocean, photosynthesis, and other processes. However, this excludes the balancing fluxes of carbon dioxide into the atmosphere from the geological reservoirs, which have slower characteristic rates. Although more than half of the carbon dioxide emitted is removed from the atmosphere within a century, some fractions, about 20%, of the emitted carbon dioxide remains in the atmosphere for many thousands of years. Similar issues apply to other greenhouse gases, many of which have longer lifetime than carbon dioxide. For example, N2O has a mean atmospheric lifetime of 121 years. Now, here is global warming potential. The global warming potential, or GWP, depends on both the efficiency of the molecule as a greenhouse gas and its atmospheric lifetime. Global warming potential is measured relative to the same mass of carbon dioxide and evaluated for a specific time scale. Thus, if a gas has a high radiative forcing but also a small or a short lifetime, it will have a large global warming potential on a 20 years scale but a small one on a 100 years scale. Conversely, if a molecule has a longer atmospheric lifetime than carbon dioxide, its global warming potential will increase when the time scale is considered. Carbon dioxide is defined to have a global warming potential of 1 over all times period. Methane has an atmospheric lifetime of 12 plus minus 3 years. Plus minus 3 means that we can add or subtract 3 according to the situation. The 2007 IPCC report lists the global warming potential as 72 over a time scale of 20 years, 25 years, over 100 years, and 7.6 over 500 years. A 2014 analysis, however, states that although methane's initial impact is about 100 times greater than that of the carbon dioxide, because of the shorter atmospheric life, after 6 or 7 decades, the impact of the two gases is about equal. And from then on, methane relative role continues to decline. The decrease in global warming potential at longer times is because methane is degraded to water and carbon dioxide through chemical reactions in the atmosphere. Now look at the natural and anthropogenic sources of greenhouse gases. Aside from purely human-produced synthetic halocarbons, most greenhouse gases have both natural and man-caused sources. During the pre-industrial Holocene, concentration of existing gases were roughly constant because the large natural sources and sinks roughly balanced. In the industrial era, human activities have added greenhouse gases to the atmosphere, mainly through the burning of fossil fuel and clearing of a forest. The 2007 fourth assessment report compiled by the IPCC noted that changes in the atmospheric concentrations of greenhouse gases and aerosol, land cover, and solar radiation alter the energy balance of the climate system, and concluded that increase in anthropogenic greenhouse gases concentration is very likely to have caused most of the increases in global average temperature since the mid-20th century. In AR4, which is the fourth assessment report, most of is defined as more than 50%. I-scores provide evidence for greenhouse gas concentration variation over the past 800,000 years. Both carbon dioxide and methane vary between glacier and interglacial phases, and concentration of these gases correlates strongly with the temperature. Direct data does not exist for periods earlier than those represented in the I-score record. A record that indicates carbon dioxide mole fraction stayed within a range of 180 ppm to 280 ppm throughout the last 800,000 years until the increase of the last 250 years. The spread of land plants is thought to have reduced carbon dioxide concentrations. During the late Devonian and plant activities, as both sources and sinks of carbon dioxide have since been important in providing stabilizing feedbacks. Earlier still, a 200 million years period of intermittent widespread glaciation extended close to the equator, which means that the snowball earth appears to have been ended suddenly about 550 MA by a colossal volcanic outgassing that raised the carbon dioxide concentration of the atmosphere abruptly to 12%, about 350 times modern levels, causing extreme greenhouse conditions and carbonate depositions as limestone at the rate of about 1 mm per day. This episode marked the close of the Precambrian eon and was succeeded by the generally warmer conditions of the Phanerozoic, during which multicellular animals and plant life evolved. No volcanic carbon dioxide emission of comparable scale has occurred since. In the modern era, emission to the atmosphere from volcanoes are approximately 0.645 billion tons of carbon dioxide per year, whereas human contribute 29 billion tons of carbon dioxide each year. Now here is anthropogenic greenhouse gases. Since about 1750, human activity has increased the concentration of carbon dioxide and other greenhouse gases. Measured atmospheric concentration of carbon dioxide are currently 100 ppm higher than pre-industrial levels. Natural sources of carbon dioxide are more than 20 times greater than sources due to human activities, but over periods longer than a few years, natural resources are closely balanced by natural sinks, mainly photosynthesis of carbon compound by plants and marine planktons. As a result of this balance, the atmospheric mole fraction of carbon dioxide remained between 260 and 280 parts per million for the 10,000 years between the end of the last glacial maximum and the start of the industrial era. It is likely that anthropogenic warming, such as that due to elevated greenhouse gas levels, has had an influence on many physical and biological systems. Future warming is projected to have a range of impacts, including sea level rise, increased frequencies and severities of some extreme weather events, loss of biodiversity, and regional changes in agricultural productivity. The main sources of greenhouse gases due to human activity are the burning of fossil fuels and deforestation, leading to higher carbon dioxide concentration in the air. Land use change, which means mainly deforestation is the topic, account for up to 1/3 of the total anthropogenic carbon dioxide emission. Livestock enteric fermentation and manure management, paddy rice farm, land use and wetland changes, man-made lakes, pipelines losses and covered vented landfill emission, leading to higher methane atmospheric concentration. Many of the newer style fully vented septic systems that enhance and target the fermentation process also are sources of atmospheric methane. Use of chlorofluorocarbons or CFCs in the refrigeration system and use of chlorofluorocarbons and halogens in the fire suppression system and manufacturing processes. Agriculture activities including the use of fertilizer that lead to high nitrous oxide concentration. The 7 sources of carbon dioxide from fossil fuel combustion are, and they are listed here as a percentage contributors for 2000 to 2004. Liquid fuels, for example, gasoline and fuel oil, that is contributed about 36%. Solid fuel, 35%, gaseous fuel 20%, cement production 3%, flaring gas industries at wells 1%, no flue hydrocarbons 1%, international bunker fuels of transport not included in national inventories 4%. Carbon dioxide, methane, nitrous oxide, and 3 groups of fluorinated gases, that is the sulfur hexafluoride, hydrofluorocarbons, and perfluorocarbons, are the major anthropogenic greenhouse gases and are regulated under the Kyoto Protocol International Treaty, which came into force in 2005. Emission limitations specified in the Kyoto Protocol expired in 2012. The Cancun Agreement agreed on in 2010, including voluntary pledges made by 76 countries to control emission. At the time of the agreement, these 76 countries were collectively responsible for 85% of the annual global emissions. Although chlorofluorocarbons are greenhouse gases, they are regulated by the Montreal Protocol, which was motivated by CFC contribution to ozone depletion rather than by their contribution to global warming. Note that ozone depletion has only a minor role in greenhouse warming, though the two processes often are confused in the media. On 15 October 2016, a negotiator from over 117 nations meeting at the summit of the United Nations Environment Programme reached a legal binding accord to phase out hydrofluorocarbons in an amendment to the Montreal Protocol. Now, greenhouse gases emissions by different sectors. Global greenhouse gases emissions can be attributed to different sectors of the economy. This provides a picture of varying contributions of different types of economic activity to global warming and helps in understanding the changes required to mitigate climate change. Man-made greenhouse gases emissions can be divided into those that arise from the combustion of fuel to produce energy and those generated by other processes. Around 2/3 of the greenhouse gases emission arise from the combustion of the fuel. Energy may be produced at the point of consumption or by a generator for consumption by others. This emission arising from energy production may be categorized according to where they are emitted or where the resulting energy is consumed. If emission is attributed at the point of production, then electricity generators contribute about 25% of global greenhouse gas emission. If these emissions are attributed to the final consumer, then 24% of the total emission arise from the manufacturing and construction, 17% from transport, 11% from domestic consumer, and 7% from commercial consumer. Around 4% of emission arise from the energy consumed by the energy and fuel industry itself. The remaining third of the emission arises from processes other than energy production. 12% of the total emission arise from agriculture, 7% from land use change and forestry, 6% from industrial processes, and 3% from waste. Around 6% of the emission are fugitive emission, which are waste gas released by the extraction of fossil fuels. Changes since a particular base year. Between 1970 and 2004, global growth in annual carbon dioxide emission was driven by North America, Asia, and the Middle East. The sharp acceleration in carbon dioxide emission rise since 2000 to more than a 3% increase per year, that is more than 2 parts per million per year, from 1.1% per year during the 1990s, is attributable to the lapse of a formerly declining trends in carbon intensity of both developing and developed nations. China was responsible for most of the global growth in emission during this period. Localized plummeting emission associated with the collapse of Soviet Union have been followed by slow emission growth in this region due to more efficient energy use made necessary by increasing proportion of it that is exported. In comparison, methane has not increased appreciably and N2O by 0.25% per year. Using different base years for measuring emission has an effect on estimates of national contributions to global warming. This can be calculated by dividing a country's highest contribution to global warming started from particular base year, but that country's minimum contribution to global warming started from a particular base year. Choosing between base years of 1750, 1950 and 1990 has a significant effect for most countries. Within the G8 group of countries, it is most significant for the UK, France and Germany. These countries have a long history of carbon dioxide emission.